All right, then. Welcome to this wonderful session about cloud events, second part, about what we do in the serverless working group. This will be a talk in two parts. Cathy, who's sitting here, will do the second portion. She will talk about workflow, and I will go and give you a bit of a deeper dive into rationale behind cloud events and how we structured the specification. You will find, I will explain the elements of the specification or several specifications that we have in brief so that you can look at the specification repo with a bit more orientation. So, as I said, Cloud Events Deep Dive, then a workflow overview by Cathy. Let me start with what events are, because that's an important distinction that also informs some of the decisions that we've been making in cloud events. Basically, events and messages look the same, right? You have data, and then you have metadata that describes that data that you send somewhere. So that looks effectively the same. And how do you decide what goes into the metadata and what the metadata is structured has to do with the intent. So they are both mailing envelopes, effectively, messages and events, for data you want to send somewhere. Events carry facts. They tell you that something just happened. So in a cloud system, you have a blob store. And in that blob store, you just create a new blob. That fact that you just created that blob is now reported out as an event, and you can react to this. So, practical example, you're uploading a JPEG file into a blob store. Now the event is raised, and now you can go and pick up that JPEG file. You can make different sized thumbnails from it and store it in your thumbnail store. So you create an event-driven flow. That is something that just happened. That is different from you taking that image and sending that to the that storage container to go and store it, because that's a command that you're giving. That is a message that you're sending. The message has a destination. The message often has, depending on what you want to do, often also has some kind of feedback that's being sent to you. So messages establish some sort of a relationship, while events are reporting about things that have happened. There are architectural consequences from this and how you build infrastructure and what the sort of metadata is that you're conveying with it. So messages carry intent, generally. Command execution, job handling, workflow progress. So that's a foundational difference that we're dealing with. Messages then have, because they are different, because they are commands, because they establish relationships, you need to have features like ways to correlate the command with the reply that comes back, right? We don't think about this necessarily when our world is HTTP, because HTTP gives us a natural correlation mechanism. HTTP has an implied correlation because you send a request and then you get a response back, and that correlation is managed effectively by the HTTP protocol. When we realize flows, message flows over different transports, may that be Amqp, may that be MQTT, may that be other protocols, then it becomes more obvious that you need to have some data in the message that says, this is this message, and that is the reply to this message, and you need to be able to correlate those two. That is metadata you need if you build a messaging system. That is metadata you don't need if you build an eventing system. So what we set out to do is build an eventing system, event-driven system of the sort that I just mentioned. A blob was created. You can go and react to that by doing a further action based on this. We're acting effectively on cascades of facts, actions that have happened in the system, rather than being imperative. We're being reactive rather than being imperative. That's an event-based flow. So Cloud Events is a lightweight convention for events. So we're not trying to boil the ocean. We're not trying to cover everything that you could possibly cover in a messaging system, everything you could possibly cover in an eventing system. But we're intentionally creating the minimal basic set of metadata and the minimal basic conventions so that we can create interoperability, because interoperability is our goal. We've had some amazing examples in the early days of the working group where people came with examples of how hard it is to deal with events today if they're not harmonized. If you don't have a common notion of what an event type is, what an event ID is, of what an event time is, and even within certain platforms, I'll just call out AWS, sometimes you have to write an enormous amount of code just to figure out which function to dispatch to. And that's because there's no standardization, not within the platforms, and worse, not across those. So we don't have reply path indicators. We don't have message-to-message correlation. We have no target address where stuff goes. We have no command verbs or methods. We don't try with this thing to be, the next version of SOAP, if that still tells anybody anything. But we're just trying to make events work, right? We're not trying to make a new messaging standard because messaging standards do exist. So what is the metadata that we need? We need a type. We need to be able to tell what just happened, to react to it. So blobstore dot blob dot created, for instance. Then we also need to be able to qualify that event further. So you need to be able to say where does that come from. So that might take the form of Microsoft.Azure.blobstore.created. But the fact that what just happened is encoded effectively in that type. And the type may also, for major revisions, also include versioning information. Then we have indication of when did that happen. That's a fairly obvious thing that we need to have time information. Then we have a descriptor for the source of the event. That is a URI. That may be an absolute URI that really designates a specific place for when that event was from where that event was raised. That may even be a network address. But more likely, it will be some logical descriptor of the entity that raised that event, right? A blob store container doesn't necessarily have a unique endpoint, but it has a URL that can go and be identified uniquely inside of the system. So it is a URI, but it's really an identifier in that sense. It's not necessarily a place that you can walk to and interact with. It's a unique identifier. Then each event itself has a unique identifier. You can go and trace it and track it, and you can also identify it and index it in the system. And then we have descriptor for the event metadata, a content type and a schema URL. The event data that's carried in that event may be text-based. It may be completely binary. And what the shape is defined by the content type of the schema URL. The schema URL is strictly optional. And the content type will tell you whether it's carrying JSON or whether it's carrying any data type you like. If you want to use cloud events to describe data that comes out of machines and that data is strictly binary in that native language of those, and what I meant was factory machines with existing protocols, you can also use that for that. Okay? So here's an example of the JSON representation. We have event formats that take that abstract data model and map them into concrete representation. So we have JSON as the core data format. So all cloud events must be able to render, all implementations must be able to render into JSON and project into JSON. And for the Amqp type system, that's the only other alternative we have right now defined, because we have an Amqp transport binding, and Amqp has its own type system. And if you are representing information in Amqp in the metadata, you need to map to the Amqp type system. And that's why we have that respective binding. Now, we have one more binding that's sitting in the group as a pull request. That is for the protobuf format, which gives us a binary option, a schema-bound binary option, so that you can also then represent cloud events using protobuf. And as I'll get to in a second, that will then be usable with every transport that we define. So think of the event schema as a way to encode an event, and you get to choose effectively which format you want. There's other candidates that we can think of that we might define still. CBOR is an IETF standard for a binary representation. It's very close to JSON. So is MessagePack and some others. I can also imagine that might be an Apache Thrift representation. So compact binary formats that fit where it is easy to go and map them. We'll have some alternatives here. But JSON is the canonical one, obviously, because everybody understands that. So this is the cloud event, as you can go and imagine it flowing across the wire. OK, so transport bindings. We have numerous transport bindings. The most important is obviously HTTP. What a transport binding does is it takes the event and now maps it into the frame of a transport protocol, or of an application protocol, to be precise in the case of HTTP. So what we do is we take that cloud event, and now we set some rules for how you map that cloud event into the headers of HTTP, how you use certain elements of the metadata in conjunction with HTTP. For instance, there is a content type header in HTTP, right? How does that relate to the content type header that we have in cloud events? And we also have different modes for how we can go and map this. You can either have the entire JSON event representation in the payload of HTTP, which we call the structured mode, or if you really need to save space, or if you have large binary payloads, then you can actually go and take that cloud event, you can explode it onto the HTTP message so that the data flows as raw binary. So it's binding to the HTTP message. That means a cloud event can be flowing on a request, and it can also be flowing on a response. What that is important for is if you have a system where you have a store that holds events for you, and you want to be able to solicit those events, you want to pull them out, of course, you need to have a way to go and project that event onto the HTTP response message where you're getting that back, and that's what that is for. We have then an overlay mechanism. Did I have that in here? I didn't mention that. Anyways, so we have an overlaid spec, an extra spec, in fact, that's called the webhook spec. And the webhook spec says, use this binding, but to deliver over HTTP, you must use HTTP post. There's an abuse feature that you need to go and implement so that you can't abuse the event push infrastructure as a distributed denial of service machine. And so there's some strict rules for how you push out an event using HTTP. So the HTTP transport binding just says, here's how I take that event and put it onto an HTTP message. And then the webhook specification layers on top of this, and that says, here's how you deliver an event using an HTTP post to a target. Here's a story for security. Here's a story for abuse protection, et cetera. That's what that spec does, sitting on top of that. OK, so structured binding mode looks like this. We have a normal HTTP post. This also projects, obviously, into HTTP2, but then it's no longer so wonderfully legible. And then you have the content type, application cloud events plus JSON. If this was protobuf, for protobuf, this will be application/cloud events plus protobuf. And then the content, the entity body of the HTTP request, will then carry the complete event information, including the data inlined into the JSON in this case, right? If you have this as if you have this in a binary format like protobuf or CBOR, then obviously the data is just a binary blob. Here in JSON, if the data is binary, then this will appear here as base64 encoding, and we have rules in the JSON format to that state kind of how you ought to be interpreting this in conjunction with the content type. The binary binding mode basically takes all of those attributes that we have defined in the core spec and projects them onto HTTP headers. So those HTTP headers are now prefixed with CE- for cloud events, which means you can easily identify them. And on the receiving end, if you're building a framework around it, as we are doing that with the SDK, you can actually go and go through all the headers. You can see everything that starts with CE-, pull them out, and then still project them and present them as normal names with normal attributes to the clients. One constraint that we made specifically also because of this is that all the names of the attributes are always lowercase. We don't allow uppercase characters at all in order to get out of trouble with uppercase and lowercase situations. So we said, instead of making really hard, complicated case folding rules, because we have to deal with transports that are case sensitive and some that are case insensitive, et cetera, we said, we're just going to constrain the character set to 26 lowercase, Latin characters. And that's also because we have so far, I'm sure we would want to expand that to other languages, but I don't know how to do this in Chinese. And then you see that the content type here is no longer for an event, but it's really just now for the payload, because the event is now exploded on the frame of HTTP, and now the payload is really the event payload. So that's a little bit more compact in terms of a format, and if you're just doing HTTP, and especially if you're doing that just from small devices, for instance, or on expensive communication lines, that's a more efficient model. With HTTP2, obviously, with header compression, you get that even smaller. And you get effectively the same effect on the other transports, which are AMQP. So AMQP is a very popular protocol for message brokers and also for event ingesters. The Red Hat version of Kafka, effectively, that sits in OpenShift, that has an AMQP head over Kafka. The event hub that we run in Azure has an AMQP head over our own very similar infrastructure. The message bus from IBM also has an AMQP head over a Kafka-like infrastructure. And obviously, there's numerous brokers that support AMQP, so we have a way to go and take that event and flow that into a message broker. There is a Kafka binding incoming, so you can go and send natively to Kafka, through Kafka. We have an MQTT binding to onboard, effectively, events, largely from small devices, so that you can go and use that mechanism and then route upstream using some of the other protocols. And then kind of in the similar vein, at the similar level, I would say, in terms of protocol fidelity, we also have NATs. So basically, from a protocol perspective, everything that's currently popular in the enterprise space, as well as in the IoT space, is covered with these transport bindings. And that was that for the deep dive on cloud events. I hope that was insightful. With that, we have our URL. We had that on the last
one.
Last slide. On the last slide, but Cloud Events spec on GitHub is the place where we have all those things, and I hope that gives you some further orientation. We're also going to have that slide deck in that repository, so you can find that there. Thank you.
Thanks. So, how how many of you have attended the workflow session at noontime and 12:15? No, okay. So how many of you have attended the serverless workgroup intro session? No. Oh, yeah. Okay. So let's see. So I think I would like to recap a little bit on the workflow. So what is a workflow and why do we need it? So many serverless applications are not a simple function triggered by a simple event. They are usually composed of multiple steps of function execution. And the functions at different steps could be triggered by different events or different combination of events. And information may need to be passed from one function to the next function or from one step to the next step. And if a step involves multiple functions, those functions could execute in sequence or in parallel. So that's why we think, function workflow is important. And before serverless, the application developer usually develop the serverless application or the functions and then run them in the developer's own system or developer's company system. With the introduction of serverless, the developer's work is now reduced to just writing those function logic. All the other work, such as managing the workflow execution steps, managing the information passing from one step to the next step or from one function to the next function, and also like scheduling, compute resources like containers to host and run those functions and do auto-scaling. All this job now is transferred from the developer's side to the serverless platform. So in order for the serverless platform to understand how to manage the workflow, the app developer needs to give a serverless application workflow spec or template to the serverless platform. So that's why we have this serverless workflow model. So our goal is to provide a standard way for the app developer to write the workflow application so that no matter which serverless platform your application is going to run on, you just need one workflow template or workflow spec. So in this session, I'm going to use a stock trade use case to show how you can use the primitives, the work group defined in the workflow model to describe this use case. So for the stock trade use case, we know that every stock trade process begins with a customer submitting a stock trade request. So when this stock trade request is received, the application or the system usually do authentication. It needs to authenticate the customer and then to interpret the trade request, whether it's a buy or it's a sell operation, and then validate the stock ticker and also check the transaction against any trading or security rules to make sure this trade request does not bend any rules. So if it's a buy stock request, the system is going to verify that there's enough money to buy the stock. And then it debit the stock cost from the account and send a response to the customer to double confirm this transaction. If it's a sale stock request, the system will verify that there are enough shares for the sale transaction. And then it will send a response for the customer to double confirm the transaction. And then the system will wait for the customer's confirmation of the stock transaction. And when receiving the confirmation, it will execute the stock transaction, update the stock account with a new number of shares, update the customer's saving or checking account with a new balance, and then set the transaction status to completion and send out notification to the customer about the transaction. Of course, in parallel, the system will update the central stock transaction statistics database with the new information. So now let's see what are the key primitives that's defined in the workflow model that we can use to describe that use case. A serverless function workflow can be naturally modeled as a state machine. The workflow may be invoked from CLI command or triggered dynamically upon the arrival of an event. So there's 3 key parts in the workflow model. So the first is a list of events. So the workflow model provides primitives for you to specify, the event triggers, such as, storage event, web request event, video streaming event, etc. There are many different types of events. And the second key part is a list of states. The workflow defined provides 6 states. The first is an event state. So in this state, the workflow is going to wait for 1 or more external events. And when those events happen, it will trigger 1 or more functions to execute. And those functions could execute in sequence or in parallel. And the second state is operation state. In this state, the workflow will not wait for any event trigger. It will just start to execute 1 or more functions which are specified in the workflow model to execute those functions. And the third is a switch state. In this state, the workflow is going to branch out to different next state. Delay state means the workflow is going to wait for a specified period of time and then transition to the next state. Parallel state means the workflow is going to execute multiple states in parallel. End state will end the workflow with a success or failure status. The workflow model also provide directives for you to specify whether those functions will be executed in sequence or in parallel. It also provides directives for you to specify retry, and as well as directives for you to specify information passing and filter. Doesn't work. Okay. So this is this workflow model to show how you can use the primitives defined in the workflow model to describe these stock trade use cases. Of course, here what we show is a diagram representation of the workflow specification. And there could be also a JSON format too. So when the workflow starts with an event state. So when the first event happens, which is a stock trade request happens, it's going to trigger function 1 to run. Function 1 will do authentication of the user, and then to interpret it is what kind of request it is, and then to check the transaction against any trading rules. And then it's going to transition to switch state. In switch state, also during this transition, the function 1's result will be passed to the switch state. So if the function 1's result is a buy stock, it's going to transition to operation by operation state. If it is a result is a sell stock, it's going to transition to the sell operation state. And then either of these operation state will not wait for any external event. It's just going to execute the function. So if it's a buy operation state, it's going to execute function 2, which will execute the stock buy operation, verify that there's enough money to buy the stock, and debit the stock cost from the account, and then send a response to the customer to double confirm. Similarly, if it's in the sell operation state, it will trigger function 3 to execute, which will execute the sell stock operation, which includes verifying enough shares for the sale transaction and send a response for the customer to double confirm. And then after that, they're going to transform to the event state. And in this event state, it's going to wait for another event to happen, which is the customer's response event to confirm the stock transaction. When that event happens, the workflow will trigger 2 functions to execute in parallel. One function is to execute the transaction and then do all the other things which I mentioned before. And the second function is to update the database with this new buy and sell information. So here are some information links. Here it shows a serverless work group link. It has information about our weekly meeting, the calling number, meeting time. And then there's under there, there's you can go to the workflow spec, We also have the Cloud Events information link. We have the spec repo too. We also have the SDK repo. That's all. Now we're open for questions. Any questions? Okay.
Yes.
Hello.
Okay. Now it's good.
Yeah, thanks for the great presentation. And there's a question regarding the workflow. Mm-hmm. So previously, we already have a lot of, the standards like the BPO or BPML for modeling or execution. And with workflow, how can we ensure, first, like the transactions, if we have some failure for the update, for example, on the orders, and can we roll back it, or how can we ensure the transaction there, and how can we ensure the interoperability with all those standards there?
Okay.
Thanks.
Yeah, that's a good question. So for the rollback, currently the workflow model, we do not go for that direction, but you can write functions, right? Now, if the previous function returns an error, you can write your own function to do how to do the rollback, because every serverless application is different. So how to do the rollback is related to the function or the application logic. So you can write the functions and stick it into the workflow, depending on the previous function execution result, and let the workflow knows, if it's an error, then invoke another function. That function will just do the rollback. Yeah. So that's how you do it.
So this is not a working group opinion, because I haven't been involved in the workflow thing. But so that model which you just described is what you will know as sagas. So sagas have an explicit way of having compensating actions for each action if the action fails. And sagas are, if you are in the cloud, a model that's more appropriate for effectively anything that you do, because the classic 2PC model, where you have these rollbacks, where you can effectively leave work in doubt for a longer period of time and then basically not make it happen, is something that that illusion works well in small constrained systems, as we used to have them on premises, where everything happened on a single box or three. The larger your systems get, the more failure opportunities you have, and of course, the more resources are being shared. And so there, you rather want to go and realize the work immediately, and then see whether you fail. And if you have failed, then go and effectively travel back and undo the effects of the work that you do. And most of that is then forward progress. If you think about what you do in financial accounting, you make a book and you add something to your ledger, and then when you realize that you have made a mistake, you add another record to your ledger to go and correct for that. So that's basically the principle for sagas, and that is also the same architectural approach. We have some stickers for cloud events, by the way.
Oh, yeah.
And that's really important, because otherwise we take them home, and that's not the point. So they're sitting over here on the table. So if you are keen to get some cloud events stickers, which are fabulous, they say cloud events, then go and get some from over here.
So since we don't have time, so we cannot take another question, but we will be here. I just want to say this workflow spec is just at its very initial stage. You're welcome to bring your questions, your use cases to poke holes. We want to make them, work for all scenarios, right? And also we welcome your participation and contribution. There's information on the weekly, serverless work group meetings. So you're welcome to join and contribute. Thank you.
Thank you.